All right, everybody. It's 2 o'clock. We're going to go ahead and get started. I just want to thank everyone for joining us today. We're here today to talk about comparing SOLIDWORKS Professional to SOLIDWORKS Premium. We will not only discuss what differentiates these products, but also some of the solutions you gain with SOLIDWORKS Premium that may apply directly to your day-to-day work. Before we get started, let me share a little bit about myself. My name is James Reeher, and I'm an application engineer at Fisher Unitech. I have a number of certifications for SOLIDWORKS and have over 11 years of experience with the software. In my previous life, I was product development engineer in a number of different industries. Let's talk about our agenda for today. We will be taking a quick look at the SOLIDWORKS product matrix. Then we will look at the enhancements and additional capabilities that SOLIDWORKS Premium provides. We will have an overall summary of the benefits, and then we will take questions. As we break down the offerings of SOLIDWORKS Premium, we will share examples that will provide you with not only an understanding of the capabilities, but also what your workflow might look like with these tools. Let's take a look at the SOLIDWORKS product matrix. We see here that SOLIDWORKS Premium has all of the tools and functionality of SOLIDWORKS Professional, including the SOLIDWORKS Toolbox, CAM, PDM, and Visualize. But it also provides enhanced 3D interconnect capabilities, motion analysis, linear static stress analysis, routing tools for pipe and tube, electrical cables and wiring harnesses, and more. We also gain advanced surface flattening tools and sustainability analysis tools. For SOLIDWORKS Motion, we're going to take a look at how it solves rigid body kinematic systems. Let's take a look at a real example now. We know that using SOLIDWORKS we can build up and visualize our design, but what about function? It's very important to check the performance of our design to ensure that it's going to meet our goals. This is where SOLIDWORKS Motion comes into play, and it will help us check the performance of our design. In this particular example, we're going to want to make sure that the Halmatra spreader can open up car bodies. SOLIDWORKS Motion is going to help us out in understanding the forces in the system and ensure that we meet those needs. We have a simple test fixture here, and we want to make sure that the spreader can apply an opening load of 20,000 newtons. We already have our assembly built up using mates, and now we just need to add a motor or actuator to drive our system. In this example, we'll apply an actuator to our piston. We'll have it move 60 millimeters, which is its range of travel. Next, we will represent our spreader load, which is 20,000 newtons, and we will apply that to our clamping blocks. You can see that we are picking and clicking our geometry selections the same way that we normally do inside SOLIDWORKS. The final thing we need to do before we run the study is that we need to define what parts are contacting. If we don't do that, then the parts will just move through each other. To define the contacts, we just say that we want the tips of the arms to contact with these blocks. There are built-in material defaults to define how those parts contact, but we can also override and make changes to those settings as we see fit. Now we will hit calculate and we'll have essentially a virtual test. This is allowing us to test our design much earlier in the design phase because we didn't actually have to produce any parts in order to make sure that our design would meet our demands. This means that we can also test out all kinds of different loads, conditions, and designs before we actually start producing anything. This saves us a lot of time and money throughout multiple phases of the design and manufacturing process. We're also getting a wealth of engineering data that will help us understand what is going on inside of our machine. For example, what is the load that we need to achieve in order to produce the 20,000 Newton spreader force? It's easy. We select our actuator and then select the plot. We're going to want to look at the forces. You can see we also have other options, velocity, displacement, etc. We'll look at the motor force in the X direction. Now we have our plot, which we see is a force as a function of time. We see that our peak force is just under 220,000 newtons. We can now use that value to back calculate what pressure we need in order to achieve that operation. We can gain a lot of information from here, including the pin loads. Motion is also tightly coupled with SOLIDWORKS simulation, so that once we have all the loading information, we are actually able to validate the stress in our components. Let's take a look at those results. This is actually a very straightforward process. We can pick any component in the system. For example, let's say we want to look at the stress result for the arm. We can then specify the time range that we want to look at the stress results over. SOLIDWORKS Motion will then go through and run the stress analysis at each time frame in order to calculate those results. We're going to take a look at the stress results for this particular arm coming up. We can see that we have the stress results over time. We also see that as we drag the timeline bar, the peak stress results update along both plot 1 and the graphics window. We see that our peak stress result is at around 2.3 seconds, and then it will lower back down as we move along. We can also look at things like factor of safety. We see our min factor of safety is about 2.2. We can also look at the deformation, and we see that it's about 0.5 millimeter. We see that we have lots of information available right here to help us size our components and verify the functionality all within the SOLIDWORKS environment. It's a great tool to make sure that your design is going to work before you build anything and minimize the number of prototypes and physical testing units. Now let's see some other examples where SOLIDWORKS Motion can be useful. We see here on this excavator arm what kind of loads we can expect with our current design. Our plots can be set up to show areas of interest. Here we are looking at plots for the bucket and swing tower. All of this has been accomplished virtually, so it's very easy to make a design change at this point in our process. Even complex mechanisms can be analyzed. Don't be afraid to design and analyze your next Rube Goldberg machine. We can even use SOLIDWORKS Motion to help us with our golf swing. Just kidding. But we can use it to help us check our golf club design. We see from our examples that SOLIDWORKS Motion provides us with a number of benefits. We save time by being able to test designs virtually and catch any failures earlier in the design process. We gain a huge cost savings not just from the time saved, but also in reducing the number of prototypes we would have made using our previous design process. We're able to gather data from our virtual testing that we can use to compare with our real-life testing. We're able to properly size components before we ever order or machine any components. Let's move on to the next section. SOLIDWORKS simulation. What exactly is it? SOLIDWORKS simulation is a set of tools that allows us to run finite element analysis, or as it is often referred to, stress analysis. What it does is allow us to look at the stresses that have occurred inside of a system based on loading conditions that we have set. All versions of SOLIDWORKS come with a basic simulation tool called SimulationXpress, but SOLIDWORKS Premium comes loaded with the full SOLIDWORKS simulation toolset for static loading. These tools differ quite substantially from one another, and we will take a quick moment to talk about SimulationXpress so that you can better understand and appreciate all of the benefits that you gain from the full simulation toolset. SimulationXpress allows you to run a basic stress analysis for a single part and only a single part. You cannot run a stress analysis on an assembly. You are also limited on the options that are available to you for setting up your boundary conditions. For your fixtures, you are limited to the fixed option, and for your loads, you are limited to force and pressure. Another point to mention about SimulationXpress is that when we look at the simulation study tree, we see fixtures, external loads, and results over here on the left-hand side. What we don't see is the mesh. This is another important differentiator since inside of full simulation, we have many different mesh options and more control over how we mesh the study. Let's take a look at some of these enhancements and how they will aid us in our design process. Here we are looking at the fixture options that are available to us with the full simulation toolset. We see that there are standard fixtures consisting of fixed, roller, slider, fixed hinge, edge, face, or vertex. We also have advanced fixtures, which consist of symmetry, cyclic symmetry, used reference geometry, on flat faces, on cylindrical faces, or on spherical faces. We can see that we now have a lot more options for fixturing our designs that will allow us to set up our study just like we would see in real life. The same applies to our external loading conditions. We see that we have many more options for our loads, such as torque, gravity, bearing loads, distributed masses, and even thermal effects. Now we're going to look at meshing options that are available to us. These include our standard mesh, our curvature-based mesh, our hybrid mesh, and our mesh controls. Notice how the mesh controls allow us to have a very fine mesh around important features. Another option that I really like about full simulation is the ability to see mesh tetrahedrons overlaid on top of my stress plots. We also have the ability to have flags attached to where the min and max stress points are located. Here we will run a quick example study so you understand what the typical workflow looks like. I've preset my material choice. Now we just need to select our fixtures and loads. Then we're going to select the type of mesh and mesh size that we want. Once the model is meshed, we then run the study and get our result plots. SOLIDWORKS simulation also gives us the ability to perform stress analysis using shells. Shells are a great tool for analyzing thin components, especially sheet metal parts. This aids in reducing our analyzation time. Simulation also gives us the ability to perform analysis with beam elements. This is extremely helpful with reducing the time it takes to run an analysis on designs that have been made using our weldment tools. In this video, we're getting to see some of the more powerful options for viewing our result plots. The first gives us an animation for the deformation. The next shows us our iso clipping and section clipping tools. It truly allows you to see what kinds of stresses, strains, and displacements are happening inside of the design. With what we've just seen, it's easy to see the benefits that simulation provides us. This tool allows us to reduce our time to market, check for failure modes early in the design process, improve the efficiency of the design by not over or under building a design, and it's built inside of our CAD design program, so we don't have to learn a separate interface or program. Now we're on to SOLIDWORKS routing. SOLIDWORKS routing gives you routing tools for pipe and tube, electrical, and ductwork. We'll look at examples of each and some of the capabilities that routing provides. In this first example, we will look at a testing machine for the Myomo grasping mechanism. We have two pneumatic cylinders that need an air supply system designed. This will include a rigid pipe from the FLR to the valve manifold. We will turn on our routing control points in the design, as we're going to create a threaded pipe route directly from the LFR to the valve manifold without placing any components first. It's simple to start a route at any control point with a right mouse click and choosing Start Route. In this case, we will use a threaded pipe and threaded elbows as the default. Likewise, we can add the port on the valve manifold in a similar fashion with Add to Route. We'll now use SOLIDWORKS' powerful Auto Route tool. It's going to generate an orthogonal route between the two segments. We can use the mouse toggle at the cursor to switch between up to 7 different route possibilities via the right mouse button. If at any time you press the left mouse button to accept, the cursor goes away. Notice also that in the Property Manager, routing now lists the number associated with each possible route, making it easier to recall the route path you prefer or go past it. Clicking within this text box brings back the new selection cursor. We will select the third route path as it meets our needs. Notice the vertical pipe's location isn't defined yet. We could dimension the location, but in this case, I want to leverage a pipe nipple connected to the valve manifold. Pipe nipples represent off-the-shelf components. SOLIDWORKS routing comes with 5 different types of pipe nipples in the design library: weld, hose, hex, close, and barrel, which we'll use for this example. To place a pipe nipple, simply drag and drop it onto the route like any other route component. Routing splits the existing pipe at this point like a T. For this nipple, we no longer need the adjacent pipe segments, so we will remove those segments. Notice that the nipple now acts as a low-cost pipe segment on its own. Now we're going to take a look at the electrical routing tools. We start by seeing that we can manually draw in a wire route. Next, we will see auto routing in action. Notice how easy routing is made by selecting the endpoints. We can also convert guidelines into routes. Now we're going to see how easy it is to merge multiple guidelines to form a harness. We can then route the harness through a clip. If we notice that the route still needs to be adjusted, we just split the route, and then we're going to drag it out using the triad. What if we want to flatten a harness for a drawing? With SOLIDWORKS routing, we actually have 2 different flattening options. The example shown is using the annotation style, which is a simplified representation of the harness. We see that this style is ideal for drawing documentation. Notice that the bill of materials contains all of the components and required wire lengths for this wire harness. Now we're going to take a look at duct routing. We're going to see that duct routing can also be auto-routed. This enables you to quickly lay out segments of the duct network and easily connect it to the rest of the infrastructure. By just selecting the start and desired endpoint, auto-route cycles through possible configurations based on the geometry layout and duct properties. Once you select an option, you can drag the route to the final desired position and complete the remaining branches to the other segments of the duct system, saving a lot of time. These parametric routes truly speed up the routing process by making changes to any existing ductwork system efficient and simple. Being able to snap branches to the existing ducts ensures everything is correctly aligned. And, of course, the auto route is supported for circular ductwork as well. SOLIDWORKS routing allows us to reduce our design time by allowing us to route virtually at the beginning of a design cycle instead of at the end. We also benefit by having accurate CAD models and drawings, which will ensure that all components are made to spec. Having these tools in the hands of the designers and engineers allows us to modify and improve our current workflows. Next up is our advanced surface capability. Many industries require flat patterns of complex geometry. For example, the label surface on this interface assembly. You can flatten any surface, including ones with internal holes like this. Additional 3D curve geometry can also be flattened like this arrow icon. You simply select the curve entities from the base surface and they are automatically formed onto the flat preview. A common challenge when designing flat patterns is that stresses are induced when forming the shape back onto the 3D surface. These stresses are easily identified using the deformation plot highlighting both stretch and compression. These areas can cause problems such as distortion and air bubbles when the label is formed onto the final surface. You can see here that modifying the original loft feature updates the flattened surface and the resulting deformation plot, giving you instant feedback into the feasibility of the design. By simply selecting tear lines, SOLIDWORKS allows relief cuts to be introduced into the flat pattern, alleviating the excessive stress around the outer edge of the label. The flat label surface is now okay to be passed on to manufacturing. After isolating the label surface and hiding any unwanted geometry, you can generate a DXF or DWG file to be sent out. You have the choice to either select geometry to export or just select a current view to gather everything visible on the screen. These capabilities take the guesswork out of creating and validating flattened shapes of even the most complex geometry. We just saw how the surface flatten tool takes complex geometry and turns it into a flat design in no time at all. This in turn makes the task of making labels for complex geometry very easy. We also see that this tool provides us with the capability to analyze the design and add relief cuts, taking the guesswork out of our label making process. Now for our last example, we're going to cover SOLIDWORKS sustainability. SOLIDWORKS Sustainability is a simple yet powerful tool inside SOLIDWORKS that provides insight into the environmental impact of your design. This example is a 5-gallon bucket, which is a common way of transporting liquids by specifying the materials, location of manufacture, and where the product is going to be used. You immediately get information on environmental factors such as carbon footprint and energy consumption. If desired, you have great flexibility in defining the specific information for the energy used, transportation components, or even the recycling components for the end of life. As you make changes, the dashboard dynamically updates to show whether the environmental impact was reduced or not. A key element of sustainability is the level of integration inside SOLIDWORKS. Using assembly visualization, you can look at sustainability characteristics like carbon footprint and clearly identify which components are the worst offenders. SOLIDWORKS sustainability isn't limited to comparing materials in a design. You can compare different designs like this bag-in-a-box approach to transporting liquids. With the cardboard box and plastic bag, the weight benefit is valuable, but what about the environmental impact? Sustainability can import any other model's environmental impact as a baseline, making comparison incredibly easy. If desired, the dashboard also allows you to drill down in more detail to see the contributions from the different life cycle phases. All the information is automatically captured in a visual report to document your evaluation and design process, even including comparisons of the worst component offenders and the baseline model as well. This makes it very easy to present your findings to anyone else in your organization. SOLIDWORKS Sustainability provides a built-in tool for analyzing the environmental impact of your design. It allows for you to compare different designs to determine which design or material choice will have the lowest environmental impact. It also provides you with an automated report generator because we know that you're very busy. So here's a quick summary of what SOLIDWORKS Premium offers above SOLIDWORKS Professional. It provides tools that allow you to verify the kinematics of your design. You're able to run static finite element analysis to validate your design. You greatly reduce the difficulty of routing pipes, tubes, wiring, and ducts for your projects. The surface flatness will take the headaches out of making labels and wraps. And the cherry on top is that you have a built-in tool for determining the environmental impact of your designs.